The motor effect is when a magnet and a current-carrying wire exert a force on each other. So if we were to take two magnetic poles like these, then there will be a magnetic field between them. Normally, this will only enact a force on other magnetic poles or certain magnetic metals. However, if we place a wire in the field, specifically one carrying an electric current, then this too will experience a force, even if it's made from a non-magnetic metal like copper. But this force won't pull the wire towards one of the poles. Instead, it causes the wire to move up, perpendicular to the field. We'll learn more about how to predict this direction elsewhere. Also, remember that by Newton's third law, the magnets will experience an equal and opposite downward force. But if they're fixed in place, then we won't see them move from this force. But why does this force happen? Well, first, we should remember that a current-carrying wire produces a magnetic field. So if a wire has an electric current flowing through it, it gains a circular magnetic field. This means that as long as a wire carries a current, it can enact a force on magnetic materials. But more importantly, if we place this close to a magnet, their fields will interact. So let's see what happens when we move the wire into the field between these two poles. The result is a very messy and complicated pattern. The field from the wire has been squashed down, and the field from the magnets has been bent around the wire. You won't be expected to recall this pattern for your exams, but you do need to know that the fields start interacting as they overlap. Then, when these fields interact, a force is exerted between them. Remember that field lines tell us the direction of a magnetic force. So here, because none of the field lines point left or right in line with the current, the force can't be in this direction. Instead, it will be up or down. In this case, the force on the wire points up, which means the magnets experience an opposite downward force. But why couldn't the force point towards one of the poles? Well, it's because the force causes the wire and magnets to move apart. You can think of this as the fields trying to unscramble themselves. If they stop overlapping, then they can go back to their original patterns. So they create a force designed to get the current and the magnet away from each other. For your exam, you need to be able to recognize when a current-carrying wire will experience a force. But how will this be shown visually? Well, 3D diagrams are simplified to only show the current in the wire and the magnetic field the wire is in. So this situation of a wire in a field would instead be drawn like this. We still have a current-carrying wire, meaning it can be affected by a magnetic field even if it is not made from a magnetic material. We don't bother drawing the field of the wire though. We also don't draw the poles the wire is between, but represent its field using dot and cross notation. Remember that a dot means something is directed out of the page and a cross means something is directed into the page. So in this case, the crosses represent a magnetic field directed into the page. In an exam, you'd be told what dots or crosses in a diagram represent. But you'll need to be able to interpret diagrams like this one and be able to identify if a motor effect would occur.
Thanks for watching. If you want to take your GCSE revision to the next level, head over to launchpadlearning.com and check out our smart learning platform that's been designed to get you top results in your exams. We cover your whole specification and make revision fun with interactive quizzes, easy to follow videos and more. You'll be kept motivated by your own AI tutor who's here to support you every step of the way. To check it out for yourself, click here. Or click here to keep watching a selection of the videos from our full GCSE Physics course. See you there!